sklearn, linear model, TheilSenRegressor. Description: TheilSenRegressor is a robust linear regression model that is resistant to outliers in the data. It estimates the regression coefficients using a robust estimator based on the Theil-Sane estimator, which is a non-parametric method that considers the slope of lines drawn between all pairs of data points. This makes it more reliable than ordinary least squares OLS regression when the data contains outliers or deviations from a linear relationship. Inputs: X a 2D array of independent variables, Y a 1D array of dependent variables. Outputs: Coa a 1D array representing the estimated regression coefficients. Intercept: the estimated intercept of the regression line. Steps: the algorithm computes the slope of the line passing through every pair of data points. The median of these slopes is selected as the robust estimate of the slope of the linear relationship. The intercept is calculated using the estimated slope and the median of the dependent variable. Metrics: mean squared error MSE measures the average squared difference between the predicted and actual values. R squared represents the proportion of variance in the dependent variable explained by K. Independent variables. Visualization plots. Scatter plot with the regression line visualizes the relationship between the independent and dependent variables with the fitted line. Residual plot plots the difference between the predicted and actual values to check for patterns that indicate model misspecification. Fine-tune parameters. Fit intercept: a Boolean parameter that determines whether to include an intercept term in the model. Random state: an integer or none, used to control the random number generator for shuffling the data. Uncertainty methods. Confidence intervals quantify the uncertainty in the estimated coefficients and intercepts. Bootstrapping: a resampling technique that generates multiple regression models by randomly sampling with replacement from the data to estimate the uncertainty in the model parameters. Challenges and fixes. Challenge 1: high computational cost for large datasets. Calculating the slope of every pair of points can be computationally expensive for datasets with a large number of samples. Sample use case: a dataset with millions of data points. Fixes to challenge 1. Use a subset of the data for model fitting. Subsampling the data can reduce the computational burden without significantly affecting the accuracy of the model. Use a faster algorithm. Some implementations of the Theil-Sane estimator use faster algorithms for calculating the slopes, such as the quick select algorithm. Challenge 2: sensitivity to the number of outliers. The Theil-Sane estimator can be sensitive to the number of outliers in the data, and the results can be skewed if the proportion of outliers is significant. Sample use case: a dataset with a high percentage of outliers. Fixes to challenge 2. Pre-processing the data to remove outliers. Outliers can be identified using techniques like Z-score or IQR interquartile range and removed from the dataset before fitting the model. Use a different robust estimator for datasets with a high proportion of outliers. Consider using a different robust estimator, such as the RANSAC algorithm, which is more resistant to outliers.